Okay, so then it got weird because then they started comparing surfaces. So it's the same setup where you have these vents that are blowing air at a given flow rate or velocity, right? These are the exact same that are going through here. Here's my force balance. So the one classic one you have right here is a smooth surface, and this is a rough surface, right? So you're measuring the difference of the forces on these, and then you take this plot, again, of just speed, where you're going from slow to fast speed in these two vents at the same time. And let's say we look at the difference of the force. You could do a ratio to see which one's more. You're saying which one's more and which one's less. So this is 0. You got this strange also behavior where you did something like this now, where the difference, or this is the smooth. So if you're below this line, this means that the smooth ball has less drag, and then above here is rough. Has less drag. So this is the peculiar thing happening when you do these external flows and comparing. If it was at low speeds, the rough one experienced more drag, something that you'd expect because roughness would you think it'd add more drag to it. Then as you increase the speed, these things would just totally like wobble, then totally sort would change. You would just change this other regime. Or if you're flowing really fast, where the speed's really high, it transitions, and then we get to this point where now the rough one has less drag on it. So, right, and that's a pretty wild, right? Totally wild. And they can compare different kinds of bodies too. So that's just the same shape where the surface is different, right? And you can take the exact same concept, right? Where now I have a sphere, and this has some sort of largest diameter, and you make this the exact same diameter. So sort of the largest dimension that the airflow sees are exactly the same in both of these models right here. You run the same thing where you just increase speed, and then you have some crazy thing as well, right? Speed right here. Yes. So then you get the same thing you had before. That we had. Only now this rate, now what's surprising is the scale of this actual force difference, right? This can get up to 5 times. So that's it. This gets up to 5 times more drag than just this streamlined body. They have the same weight and they have the same dimension, but just with this simple experiment, you have the same procedure, only this scale now blows up. So it's another phenomenon. And then what other you could do, they got so interested in this strange airline or streamline shaped body, you could even just take the actual sphere off completely. So then all you have right here is just a square bluff metal bar, right? If I zoomed in here, it's just a metal cylinder sphere. And still, even with that, you could see that there was a non-zero situation that was going on. It was like this, only now this is almost like a scale of 0.1, but there's still a difference. This still experienced more drag than this streamlined body, which is just wild to imagine because in terms of before we measured the sphere had the same diameters, this isn't even that. I mean, these bars that you could measure, sometimes they're a tenth of the diameter. So if this is D, right, this width is actually like 10 times less the width, but it still has experienced more drag than the streamlined body. So we don't have quite much to describe what's going on. So that motivated that we needed some understanding of what's happening on the external surfaces of these things. And then the story gets even worse when we started changing the fluid, because always this was just air that were flowing through there. So, right, it stands to reason we can change the fluid and see if these results still hold. So that property we did 2 big tanks. Right, and these are filled with glycerin. Right. That's a very viscous fluid, right? And then we dropped very small things in there. So this is tiny diameter, and then same one. Same process that we had for the big air vents, and then we made little tick marks on the side of these giant. Right, these are just big bases right here. Here's the bottom. So then it came down to, well, now let's take these smaller ones, but they still have the same characteristic dimensions, drop them in tanks of glycerin, which are very viscous, and look at the drag or something that's happening there. So they drop them in there. They don't start measuring till, let's say, they get past here. And that here, that's when you reach terminal velocity, meaning that the forces balance on there. Then they would tick along, so go 1, 2, 3, 4. I think you do this experiment in fluids 1, but that's what you're measuring. You let it sit by here, you have a stopwatch, go bang, tick, tick, tick. It gives you an idea of velocity. After it reaches this point, terminal velocity means that the forces balance on it. So that means that the drag force must balance the weight force of these 2 objects. So this is that the sum of the forces equals 0 in this situation. So if one has a higher velocity, if one's falling faster, one of these objects is falling faster, right? Right, that means it has less resistance. It's falling faster, it's experiencing less resistance to the flow. So what's the result now of comparing this small diameter to this teardrop shape? Remember, in the air, this one wins by a long shot. It experiences far less drag. But when you do the ball compared to here, what should I call that? In the very viscous fluid, when we do the exact same experiment, right, the sphere drops way faster than the teardrop or the stream body. So that's the exact opposite behavior that we observed when we did this over at air vents. It's doing 100% the inverted case. And then you could do this thing where they just compared them bigger. Right, they did this a bunch of times and compared many, many different sizes and shapes, dropping them in these glycerin tanks. And then what they could do is you could find 2 of these that have correlated the same velocities and then calculate drag forces. And that's right. So before I was talking about velocities, if the one's falling faster, but you could do it this way where you kept dropping all of these combinations and you look for the weights that match. So let's say like there's this one have follow the same velocities. And then still, you would still conclude that the drag force on, like, as a function of teardrop, right, is just enormously bigger than the drag force as a function of the sphere. So this is just highlighting how the exact opposite of what we think is happening occurs in external flows with very, very simple experiments. I'm doing the same thing I did with the air vent, I'm just dropping it in these tanks full of glycerin, which is high viscosity fluids. So I was highlighting some very non-intuitive things that happen in external flows. And then we can come to now basic experimental laws that you can determine just from these relationships and plotting a bunch of things.